In this video, we are going to compare a linear analysis with a nonlinear analysis in SOLIDWORKS Simulation, using this pipe structure as an example. Since the geometry and loading are symmetric, symmetry can be used to reduce the model size and make the analysis faster. First, we will load the pipe using a regular linear elastic analysis. When you choose static analysis, by default the model type is linear elastic isotropic, and this means that the material follows a straight line relationship between stress and strain, so you only have Young's modulus, and when you remove the load it returns to its original shape. But this is not oftentimes correct if the loads are a little bit higher and the stresses exceeds the yield point. Then you need to do a nonlinear study. We can use, for example, plasticity with one misses, and this means when you exceed the yield strength of the material, you go to the plastic region, and when you unload this you have a residual plastic strain. You have a permanent deformation, and this is permanent deformation we are going to look at for our example. We are going to load this and unload this and see how much the deformed shape is deformed when we unload the part. Okay, so you can go to simulation, new study, create a static study, and you can apply the material here. This is a linear elastic study. The model type is linear elastic isotropic. Isotropic means we have the same material properties in all directions. Fix the geometry here, press OK, and we can go ahead and apply a load here, external load. Right click on that, bearing load. I have created a coordinate system before, so, and the Z direction is pointing in the axial direction. 22 kilonewtons. We can apply this in this direction and press OK. Apply the symmetry. Sometimes this is annoying when it comes up. You can go ahead and task plane, uncheck this and apply the symmetry here. Right click, advanced, and symmetry. Go ahead and choose this surface, and bam. Now we have the symmetry, the load, the boundary condition. Now we mesh it. Create the mesh. Create mesh. Do a fine mesh. You can apply mesh controls. There you have the maximum stresses and boundary conditions and where the load is applied if you want. Here I only use mesh control here. Not super necessary, but it's sometimes good to have a better result. You see the mesh right here. Yes, and you can go ahead and run this study. This is our linear elastic study. and right click on the stress, edit definition, true scale, and display symmetric result to see the whole part. And you can see the maximum stress here. You can by using space you can choose the right angle to see from the top, and you can see the maximum stress here. It's a little bit too high, it's 997, and the maximum displacement, if you go ahead and display symmetric result, and you can see from this angle it's 36.2 millimeters. This is a linear study. When we do a non-linear study, the stresses are going to be lower, and the displacement is going to be a little bit higher. So we can create a new study, this time a non-linear study, static or dynamic. We choose static. And drag this, and you can copy the everything. You can copy the load, the boundary conditions, the symmetry, everything you can copy and paste. Sometimes it's better if you do it, if it's paste everything. We have the fixtures, load, meshes. If it doesn't take that much time, you can do it by hand and not copy. Sometimes it's giving warnings, but it's okay. You can create the mesh. This is exactly the same mesh, and you can look at the material here. SS in the alloy steel, SS in parentheses. This means that you have a stress strain curve here, as you can see. And we had the plasticity, model type was plasticity, one misses. So run this study. This is going to be time consuming, and this warning is nothing. It says don't close the active model. This is going to take 3 minutes, and when this is done, you can go ahead and look at the results. You can see here the stresses are much lower. We had 997 megapascal, now we have 682. So lower stresses, and the displacement, we had 36 before, now we have 42, a little bit higher displacement as expected. You can go ahead and display their symmetric results if you want. And this nonlinear study is done in steps, many steps. You can see step by step the load is applied, and the deformation here is shown. You can go ahead and choose the load, variation with time. You can choose curve here, and here you only have, in 1 second you apply the whole load linearly. Now I'm going to apply the load in half a second, and then in the other half unload. So I'm going to call this load and unload, just to be clear. Load and unload. Then we are going to run the study one more time. and see how much the permanent deformation in millimeters we get. So don't forget to like and subscribe. Yeah, this is going to be a little bit more time consuming, 5 minutes, for my computer at least. So you can go ahead and do the same stresses and displacement we get here, but the steps are different. So the last step is when we unload this, and we had 17 steps. So somewhere in the middle you have the highest displacement, 42.3, somewhere in the middle. Yeah, step 9. So step 9 we have the highest displacement and stress. Step 9. Here you can see how the load is applied. This load is applied in 1 second, and in this second we have 17 steps. You can look at the displacement too, and you can get a feeling of how this shape is deforming. So in the last step is the most interesting. So when we unload this part, the permanent deformation in millimeters is 5.5 something, 5.6 millimeters. Yeah, this is the permanent deformation. So these are the final results. Lower maximum stress and a higher maximum displacement for a nonlinear analysis, and a permanent deformation of 5.6 millimeters. Thank you.